Good morning, YouTube. Once again, here's a continuous video for the NEC reference book or National Electric book. This is for basically electrical engineers wanting to test out for the Power PE exam. So once again, this videos that I've been creating is really for a self-reference for myself, but I decided to share it with everyone else in regard to the NEC in preparation. So the goal here is to just kind of remind myself the shortcuts of the tables and the sections that I need to reference that is probably most common to be utilized during the exam. So chapter 4, I decided to dedicate a dedicated video just for chapter 4. I didn't cover all of the sections, but only mainly the main ones that I believe are commonly used. So for chapter 4, I think the takeaway here is understanding the ampacity in the motor rating determination. I think one of the most common thing that we will see all the time on here is these are the tables that must be referenced during the time you search and maneuver through chapter 4. I think one of the main ones is really 31015 Bravo, but we'll go through the list. All right, so one of the first tables that you want to familiarize yourself with is table 430.7 Bravo, which is the locked rotor indicating code letters. So based on the motors, how it's rated, based on the code letter, you can actually calculate the total kilovolt ampere kVA per horsepower. I think the best takeaway here is please don't make the mistake that I do all the time, is make sure you read and understand what the table stands for. So this is kilovolts, not just VA. So given the horsepower of the motor based on the code letter, and you were to determine the kVA or the VA, just be mindful that this is in kilovolts, so it's in the thousands already. So if the multiple choice gives you in the thousands, like let's say 1000 VA, and you somehow solve for 1 kVA, just know that they're the same. Part 2 is motors, circuits, conductors. So how to determine and how to size the correct conductors for the motors. So in this case, for a single motor, looks like for conductors that supply single motors used in a continuous duty application shall have an ampacity of not less than 125. You're going to see this a lot. You're going to hear this a lot. So this is definitely something to keep in mind. Not sure why I did that. So let's go ahead. Single motors. Okay. For a wound rotary secondary, I think this is very important because I think we've dealt with this in section or chapter 2. So continuous duty. For any continuous duty, conductors must be connected. Then it must be at minimum 125% of the full load of the secondary current of that motor. So I'll go ahead and highlight that. So other than continuous, that's fine. I think what I wanted to highlight in this section is section 430.24, where you have several motors or a motor and other loads. This is a very important section because you might see something like this where not only you have just a single motor connected, but you have multiple motors and maybe an additional load, other loads that are not motors connected to this, and you want to measure and size the correct conductor. You must follow these 3 procedures right here. Steps. I think the takeaway that I want to highlight for myself is that it is always 100% of the non-continuous non-motor load, and it's always 125 for the continuous. And what it is it would be the sum. So I think here says sum of the full load current rating of all the other motors in a group as determined. Okay, so They do go back and forth with between sections, so please just make sure you read the entire sentence and follow through. But I think the takeaway here is if you have continuous non-motor loads, you must do 125. If it is non-continuous, then it will be just 100% of it. So let's see here, 125% of the full load current rating of the highest rated motor as determined by 430.6a. So, okay. Part 3, this is for branch circuits overload protection. And then you have part 4, which is for the short circuit ground fault protection. Very important tables and sections that you want to really reference here. Once again, for 430.32, continuous duty motors, more than 1 horsepower. Each motor is used in a continuous duty application. 1 horsepower shall be protected against an overload by one of the means from 1 through A. So I think I have the section here, as you can see. So motors with a marked service factor, 1.5. This is all great to kind of keep in mind depending on the situation you're running into. So you might run into a motor with a marked temperature of 40 Celsius or less, then you would have to use this concept. So you would have to multiply it by 125. All other motors, it would be 115. Okay. So for motors that are not over 1 horsepower, so any motors that are less than 1 horsepower without individual road protectors shall be permitted. So I think the takeaway here is that any motors that are less than 1 horsepower can basically be connected without an overload protection. This is really important. In the end of this video, we'll go over like just an example to kind of see how to reference this table, but you will run into this. So the maximum rating on settings, so these are the numbers that you see, the values that you see here, these are all percentages. So depending on what you're solving for, instantaneous, time breaker, or any of them, just keep in mind that the values here, they're all percentages. So if you get the full load current of a motor and you want to know what the inverse time breaker setting, depending on if it's a single phase, a squirrel cage, synchronous, wound rotor, whatever the case is, these are your percentages. So if I'm dealing with a single phase, then I would use 250% of that full current. And then whatever that ampacity, then that will give me the size of that inverse time breaker. But be mindful, you must go follow through in chapter 2, where there's like a standardized fuse sizes that it's important to follow, because it's not just the exact ampacity that you calculate for, it's the size that you want to pick for. Okay, so what are we looking at here? So the ampere rating of the interrupting capacity, let me see here for combination loads. Okay, for torque motors, disconnecting means. So I think this is something that we're going to probably see a lot. It lists unfused motors with a horsepower rating and less than a motor horsepower shall be permitted to have an ampere rating less than 115 of the load. Okay, so disconnecting mean for a torque motor shall have an ampere rating of at least 115%. This is good. 2 motors are used together, or whether or 1 motor used, that load may be instantaneous. So here's the continuous here, horsepower rating, the full load current. Okay. For small rotors not covered by table 430, 24/7, 247, 248, 249, or 250, the locked rotor current shall be assumed to be 6 times the full current. This is interesting. So for small motors, now the question is, what are considered as small motors? But just keep this in mind as well. Just know that chapter 4, section 430 heavily is focused on motors, and that's probably the main section that we're going to really focus on. There are other sections in the chapter 4 that we have to keep in mind. Honestly, the whole thing is important to go over and get familiarized with. But section 430 specifically for motors is the section that we really need to focus on. So followed by those tables right here, table 247 is going to be the full load current in amperes, but for DC motors. So if you're dealing with DC motors, then this is your table that you need to reference to figure out, based on the horsepower given, what is the actual amp rating of that motor based on the voltage that's connected to. 430, 248 and 249. 248 is for a single phase AC current motor. And then you have for a two phase. So if you're given a scenario to solve for an AC single phase motor, then this is where you would have to reference based on the voltage that it's connected, given the amperage. Same thing for the two phase. The most common table that you're going to see, or you're going to really highly recommend you familiarize yourself with, is table 430, 250. This is for the full load for a three-phase AC motor. Keep in mind that this is the National Electric Code 2017. The current of this recording, the exam that I'm preparing for, that I wanted to take, is basically they're referencing the National Electric Code 2017. But there are newer versions. I'm not quite sure when they'll use, but when that's released, just be mindful that this is based on the 2017. All right, so the difference here you need to keep an eye on is you have the induction type squirrel cage and wound rotor, and then you have the synchronous type unity power factor amperes, etc. Okay? Familiarize yourself with this table. Get used to it, because this is where you're probably going to come to all the time whenever given a motor problem and you want to figure out what the total ampere based on the voltage that it's connected to. Okay, here, conversion table of a single phase locked rotor. So this is kind of like a table right underneath, but just keep in mind that this is for a single phase locked rotor. So if you're given a problem, wanting to know what the locked rotor is for that specific single phase motor, this is the table that you want to look at. And then followed by the next page, table 430, 251 Bravo. This is for a polyphase design BCD maximum locked rotor. And this one you want to be mindful of that it is utilized for a three-phase. Selection of disconnecting means control is determined for horsepowers and voltage rating. Design letters for use. Yeah, so this is going to be for your three-phase. There you go. This is what I was looking for. So that's for your single phase. And this is for that criteria, but in reference to a two and three phase motors. All right, in this section, 450.3 overcurrent protection, very important section in regard to a separate device, I believe. So let's take a look. I think this is actually, so I take that back. Going back to this section right here, I forgot to mention, I should have gone the previous section, but this is a protective device for a separate, oh, here we go. A separate overload device. That's what I meant to say right here. I think I forgot to cover this. For a separate overload device, this is a criteria you want to follow. Okay, going back to our section right here. So overcurrent protection, I believe 450 covers more for transformers. So this is a section that not as common, but in case you run into it, when you hear the word transformer, auto transformers, and you need to figure out the overcurrent protection for it, this is your section, 450. So what do we have here for 450? Transformers over 1,000 overcurrent protection shall be provided in accordance with table 430.A. Okay. Transformers 1000 volts no more or less, overcurrent protection shall be provided by table 430.B. Okay. And voltage potential transformers, and then auto transformers 1000 volts nominals or less, overcurrent protection. Each transformer 1000 volts, as you can see, shall be rated or set to not more than 125% of the rated full current of that auto transformer. For transformers over 1000, follow that table. For transformers less than 1000, then follow the or 1000 or less, follow 430.3 Bravo. Okay, so here's our tables. Table 430.3A. So here's your location limitation, any location supervised. These are important to take away, so where it's located versus supervised, and then transformer rated no more than 6%. So given the impedance, if it's 6% or less, or if it's more than 6%, here are your criteria that you need to follow. Okay. What I'm going to do is just a giveaway. Let's go ahead and just answer a question just to see, based on the section that we covered, how to tackle this problem. So you have a 3-phase 20 horsepower induction motor. Basically the nameplate is a single speed, 460 volts, 20 amps, 118 RPM, and a 1 power factor being served by a branch circuit. Determine the best suited instantaneous trip breaker size to protect against the short circuit and the ground fault. So right away, giving from here is we need to know the instantaneous trip breaker size. What is the correct size for it? The takeaway here you got to be careful with is you have a 20 horsepower induction motor, and then you're given the nameplate. They're giving you 20 amps, but there's a section you want to read and look at. Based on this given question, we do not follow the 20 amps as our full current. That is not the case. So what are your answers? Need additional information? Obviously right away with all the given information, there's too much information that we don't even need. So right away, process of elimination, we know for a fact that it can't be that. Now you got 60 amps, 216, and 225. The section you want to look at is 430. I think this is a section 430.6A that basically says that you do not need to go by the nameplate, but you must follow that table, our famous table, which is, because it's a 3-phase, we're going to look at table 430.250. Okay, so this right here is going to give us for an induction motor, we need to figure out for a 20 horsepower, what is the full current. So if we take a look at that table, I think I have it on here. So let's take a look. So here's your induction type motors. And I think the question was rated at, it was a 20 horsepower, and the voltage that was connected, it was at 460. So if you take a look at 460 here, go down the list, and at 20 horsepower, your rated is 27. So 27 amps is your horsepower.